learning more from the center. So again, thanks a lot for having me over here today. My talk's title is Brain Inspired Computing, the extraordinary voyage from known to unknown world. Essentially, I felt like research itself and can be taken as a voyage and from known to unknown worlds, and therefore I always like this title for my talk. Give me a second. Okay. So let me start, and I don't know how many of you have read this in a series of book. When I was a little girl at the middle school, actually it was a very popular book series, and the Extraordinary Voyage in Known and Unknown World. And the book series is starting with the Paris to the journey to the center of the Earth, and then further from the Earth to the Moon. Essentially, again, I feel our research follow the same thread, and we're looking forward some ideas and out of box and trying to extend our research scope. This is another page I always like to present. In fact, the first time I saw this page presented by Dr. Hilton from UCSD back to 2016. But still, I feel the information on this page is valid and variable. Many years ago, when I started my college studies and people use in desktops and workstations, as you can see, it wasn't very powerful compared what we have in nowadays, and those mainly used for personal computing, and the machine to machines are connected through wired internet. So the question is, what happened after so many years, and what are the major changes in these years? So one dimension we illustrate over here is from programming to learning processes. So old days, and we need to program and make the desktops or workstations and function as expected. Well, towards to AI machine learnings, armed with the data center and cloud, we are able to collect and integrate a lot of data. We are able to provide a large scale storage and the computation elements so that to analyze this and those data and discover new informations. So computing system from kind of a large scales is changing from programming to aggressive and learning process. Another domain I think is very interesting is the change from static offline virtual world to more dynamic and online real world. Well, if you compare desktop in those days versus a mobile phone, currently the mobile phone itself and could be more powerful than the desktops in 20 years ago in terms of the computation. But beyond this, and the mobile phones and having sensing capabilities, it has a display to interact with the users. It's able to connect with the tons of devices to wireless communication and the internet. And of course, as I mentioned, they provide more and more powerful computation capabilities, even just at the phone itself. And more than that, in fact, nowadays, and we have many large variety of kind of edge devices and for different functionalities, and that's developed in very diverse intelligence and system or intelligent world that we can leverage. Well, in order to enable a very intelligent world for various functionalities, and I guess one of the challenging tasks is to achieve efficient computation and the data analysis capability. Well, usually when we comes over here, if I presents to dedicating hardware audience, and we can down to explain what is lacking in the current hardware systems. And but here I will jump off this and explain, hey, what is our ultimate goal? My research is very similar as in Corey's research. We seek the very efficient computing machines so that we are able to achieve an highly intelligence. Well, our ultimate goal, in fact, to achieve the level of our human brains. So when we're talking about the human brains, it's composed to 30 billion neurons. It has an extremely complex structures. Well, I mean, very higher level, we say it's made with a white matter and the gray matters. And if we zoom into that, the neural cortex and having 6 layers, and the signals can travel within and between those layers. Well, if we can go even into finer granularities, and this is people kind of understand their neurons to process signal from other neurons. Well, synapses are used as a memory and provide waiting functionalities. So compare the brain and with our current computing systems, and there are three key characteristics and that to be boosted up. And so one is very low power consumption. Another is the fault tolerance and kind of a self and recovery mechanisms, and of course, and the capabilities and of cell programming or adaptivity. So back to the theme of my talks and from known to unknown world. I mean, the brain structure or capability is our ultimate goal. There are a lot of research activities along those directions. So particularly in our groups, and we address the situations and for currently AI machine learning approach like DNA accelerations. We also interested in what's falling, what's going to be variable in the future. For example, how can we leverage a new emerging device like RAM to rebuild the computing systems, so-called the neuromorphic designs. And beyond that, for the entire intelligent systems, we also curious what are challenges and opportunities and to further persuade. So I will give in this and three examples in today's talk, and the talk itself and can go through pretty quickly. But if you have any questions, then feel free to contact me for further discussion. All right. So let me start with pruning and sparsification for deep neural network acceleration. This serious work was based on existing commodity hardwares and like GPUs and CPUs, FPGAs, and even RAM-based designs. So one critical situation when we're talking about high efficient design is, the large DNA models and cannot be accommodated or realized on hardwares and very efficiently. In fact, what happened is, and when we tend to increase the accuracy, performance, and for the DNA models, it's easily grows very, very fast. Well, first of all, the parameters of the NNs are grows extremely fast, but meanwhile, we find that those parameters, many of them are redundant. So the question is, can we reduce the parameters or activations and therefore reduce the computation and the bandwidth requirement? Well, we actually start the thread of this work back to 5 or 6 years ago. Um, early stage, and a lot of people work on algorithm levels and already trying to conduct some sparsification, studies. Well, compared to what we call the non-structured sparsities, and our work focus on structured sparsity. So what happens really is an non-structured sparsity is basically based on the algorithms discoveries and tend to remove those parameters with a smaller amplitude, meaning they play less importance during the data processing. Well, when we realize those data on GPU and CPUs, and what we find is, and although like demonstrate on this purple curve, the sparsity levels across and convolutional layers and pretty high, kind of close to 100%, like more than 90%. A lot of times the speed up is very marginal, and for some layers, and there even incurs performance and degradation. This is mainly because of a non-structured specification doesn't consider the hardware execution efficiency, and therefore it's created complexity when mapping to the hardwares. So encoding and decoding sometimes introduce an even higher latency and overhead. So what we proposed is called the structured sparsity. The goal over here is, and for example, for this in matrix operations, and we tend to remove the entire row and entire column. So once sparsification has been conducted, the entire array can be squeezed into the small dense structure, which is then friendly for the hardware like data storage and the computation. Well, this work actually has been done, for many years, and there are a lot of different variety versions and very higher levels, and the structure sparse and DNNs, and the key over here is define and group. And when we're talking about the group can be any forms of a weight block. And a lot of times, and I'm telling the students, and you as the users can define those groups and based on your need. For example, in CNNs, the group of the weight could be a channel, it could be a 3D filter, could be a 2D filter. It could be shape-wise and fibers, and it could be even the entire layers. It really depends on the model you have. Also depends on the data set and your applications. So you could try different combinations and find the best for your application. Well, once you define the groups, and the next step is pretty simple. We can apply group lasso regularization, and this is all you need. Basically, we first split weights into groups as explained on the previous page, and then we add group lasso on each group, and then sum those group lassos and over all the groups and apply them as a regularization. So the SGD optimization becomes since two. One is the original loss term, and another is an group lasso regularization, and this helps to realize the sparsification in a structured way. Okay. So this interact word has been applied since to CNNs. I know the figure here is pretty small, but here we compare the non-structured in orange color and the structure in the green color approaches. So as you can see, if we just looking at the sparsification rate, structure sparsifications actually has a lower efficiency compared to the non-structured. But if you're looking at hardware execution speed up on CPU and the GPUs, and those blue bars, those green bars are much higher than the orange bars, means we can really achieve hardware benefits. So when we try the structure specifications, and in fact, we applies to LSTM, we applies to RNNs, and recently we also applies to the 3D VIT models. So all these models, and first of all, they have redundancy, And second, we find that then structured ways and can represent the data pretty well. So the key is and how do you define the groups and how do you discover the essentially important part versus and those redundant part. The methodology also being adopted by a number of the companies and in different ways. So when we moving beyond the lassos and later on, and we're trying to understand what's essential when we removing or removing redundant weights. So one of the observation, in fact, is a lot of specification techniques in trying to remove those weights with the smaller values. In the training processes, and we find that when we are doing this, and a side effect is, and for all this and large weights, and the trend is also kind of reduce their amplitude. So those important weights and kind of also getting smaller and smaller, and this definitely is not what we want. So actually we actually explore what we call the Howyer approach. Um, and the goal is to find the regularizer that both and differentiable and skill invariant. And here actually is the optimization regularization applied over here compares to the group lassos. It's changed to the square root of the L1 and L2 ratio, and it becomes differentiable and the scale invariable. And then with the group definition again, we apply Howyer square regularizer over L2 norm and form the groups. The remaining are similar. I will skip the details and for today's seminar, but just to show one example here. So one observing the gradient of the Howyer square regularizer with respect to each element in the weight matrices, we can say this subtraction term, this is induced an auto trimming effect. What is the auto trimming effect mean over here? Like illustrated in this figure, x-axis is the trim epochs and the y-axis is the weight values. And each curve represent one random sample weight parameter. So as you can see on this and grade descent path, and during the optimization, the regularizer will turn weights with smaller absolute value to 0, like those ones, and becomes to 0. But a large weight that higher than the threshold will kind of reduce their degradation rate and trying to kind of maintain their values. So the trimming threshold here actually indeed is this black dash lines in the figure. Okay. So with this Howyer square regularizers, and we are able to achieve an even better performance, and which I omit here. Well, beyond this, we also interested in the missed precision. Particularly this work, we're looking forward the applications to RM designs and for some finer level designs. And so essentially, we aim to select the optimal precision for each layer. And in this approach, as you can see, a lot of DNN implementations right now already switch and from floating points to fixed point. So we were wondering when can its precision be reduced? And I mean, if we're looking into those and ways represent in the binary ways, if an MSBs are 0 for odd elements and the precision can reduce indirectly, if LSB is 0 for odd elements, and then the precision can be reduced with the scaling factor 2, like we illustrate over here. So this thread work is talking about the quantization it's using structure bit level specification, but essentially it's achieved in a quantized representation of the weights. And since the bit level specification, as we analyze this, then can be conducted along the bit level in a very finer granularity. So layer by layer on the DNA models, and they could achieve a different level of the sparsity. Well, as you can see, when we are doing this, and the grouping becomes to the same bits and across the weight parameters, and within same matrix or within the layers. Um, Here actually are kind of some results. And so for bits representations, and we follow the dynamic scaling quantization procedure, and then we use element with the largest absolute values in each layer as the scaling factor. So in this way, we are able to realize the normalization across the parameters within the layer and ensure the performance. So during the trainings, and we allow each bit to take continuous value between 0 and 2. And this is mainly in order to achieve the better differentiabilities. And then we apply the STEs where it estimated actual quantized value. Um, and the remaining processes is very similar as an STE, but we are able to obtain extremely high quantization levels and higher executions on the hardware level. So this is a very quick kind of a introduction on our works on how to achieve the pruning specification and extend it to some quantization schemes for the DNNs. Well, my second quick topic is RM-based and neuromorphic chip design. Okay, so along those lines, and I mean, the previous one is built based on the existing hardware. We are able to push the limit, but as you can see, the best we can achieve on the existing hardware is there. So a lot of researchers are working on how can we leverage new devices and build new circuit and architectures for the next generation computing systems. Well, many years ago, I guess in 2009, um, people rediscover memory stir technologies, and were realized, a lot of them realized that by RAM, resistive random access memories. So at the time, some people find that for this and two-terminal device, if we apply a large current or voltage across the two terminals, we're able to change the resistance value. Well, if we reduce the current or the voltage to a lower levels, and then we are able to get this and resistance and read out. So higher level behavior wise, and we can take these devices as an programmable resistor. And the unique advantage of it is it can provide analog states. Or more than this, and when we work on kind of an integrated structure of the memory devices, and since it is an oxide structures with the only two terminals, and it can be realized then by this and what we call the crossbar structure. Essentially, we can have a one layer of the mentals and horizontally, and another layer of the mentals and kind of orthogonal to it. And then at each cross point, we can make one memory stir device. So at higher level, the structures, and we can apply voltage from one direction and detecting the current from the other detection. This functionalities, and again, it's very analog to the matrix operation, like supply and a vector along one directions, and then the output, in fact, is the weighted summation of the weighted of the input factors, and the weighting factor is the conductance of those devices. And this also analog to the synaptic weighting function as well in a very high density. So with those observations and things and more than 10 years ago, I think in Corey was at the Air Force at the time. I was at Air Force Research Lab at the time. So we start discussing utilizing memory stir crossbar arrays and for computation. We start with a simple example called the bring state in a box, and we're trying to realize this recall and training functionalities. Well, one of the reasons and we use in bring state in a box and BSB is it is an kind of an iterative process. So it has a higher resilience to the noise and the variations. So as a starting point, and it's pretty nice and for the demonstration. So as you can see at the starting points, and what we have is these represent memory star crossbar arrays. So we feed the input vector to the crossbar array. And in the first version of our designs, and we use two memory star arrays because in mathematical representations, and the matrix A is entry could be positive and a negative. While memory star crossbar array as in physical representations, and they can only have positive weights. So we use two of them corresponding to positive and negative part, and then use some summing op amps to perform analog voltage signal addition and subtraction to generate the output. We then compare the output with the previous one and say whether they converged or not. If it's not converged, then the compute output will be supplied by replacing the input vector. So we can initialize this iteration. The iteration stops once the input and output vectors are identical to each other. So this is the general realization of the BSB functionality. Um, of course, in so many years, and there have been a lot of changes and improvement in these designs. So one of an interesting work we have done is instead of to have an voltage level that's the inputs, we try to understand, can we switch that to the spikes? Well, exercise and shows that and it works, but not as ideal as in kind of a linear correlations. The reason, in fact, is in the real computations, and especially in measurement, we have to consider the plastic impacts, where resistance and capacitance, and also circuit response times. So it becomes an kind of monolithic relations, but not exactly the linear relations. This is the difference between the physical implementation and also theoretical analysis. Well, afterwards, and in fact, we conducted a lot of circuit designs, and due to the time reasons, I don't jump into the details. But this basically see that when we do the physical implementations, we have to be very careful in the design. Only IFC is not sufficient. We in fact included current amplifiers in order to stabilize the voltage at the bit lines. And we tape out the chip, do the testing for MNIST and Cepher 10s, and do a lot of measurement. The results and corresponds to the expectation. We further study, hey, can we push further for this and spiking based designs? And instead of to apply the rate, like a frequency for the data representations, can we using the timing to represent the data, can we using one single spike with the timing information to represent the data and for the data processings. And therefore, ReSPIKE was the work we published in 2020s and to achieve this goal. As you can imagine, when we only use one single spike for data transition and the processing, the power consumption could be extremely low. So those are kind of circuit level realizations. We also move up to the architecture levels to analyze this. And if we like to build accelerators and for example, MLP and CNN operations, and what is the analog and what we do. So our HPC Works was the first one for RM-based accelerator designs. It's discussed the kernel mappings and the interlayer parallelisms. And later on, the hyper is talking about at higher levels, and when we build a chip with the multiple accelerators, and then what's the optimal mapping schemes and per layer, whether whether this is in data parallelism is a better or model parallelism is better. And in fact, what we find is depends on the number of the accelerators and also hardware topologies and a combination of the versions, and in fact can provide the best performance. Defects and the recoveries and always, and like reliability issues is always a concern when we're doing the study for the emerging devices. In fact, this is one of our early testing results, and when we work with the HP labs. So at that time, many years ago, as you can see, the yield is pretty low. Basically, the yield map shows only around 85% of the devices and perform reasonably normally. And among this, 15% of kind of defective devices, most of them are stuck on defects, and a small number of them are stuck off the device. So at the beginning, so we're trying to analyze this, hey, for such kind of a large and defect rate, what do we do? Can we find out from network levels and what's the contribution of those on weights? Some of them are more important than the others, and then can we remapping and better utilize those good devices? And of course, and recently we come out and this in more systematic ways. And the idea over here is for DNN implementations, we can intentionally inject a certain errors and during the training processes in order to improve the final tolerance in terms of the variation and the noises. Well, if we keep doing this, and the training will take forever, simply because the variation combination is unlimited. So in order to have better predictions, and the key over here is to optimize the stretch rates to find the right hardware configurations. So we applies the multi-objective optimization MMO methodology over here. So for example, all the points over here show lines the Pareto trend, and we tend to avoid very high latency or very high energy designs, and based on the criteria, the budget given by the designers. And so those are kind of the optimal designs, and with the different trade-offs in terms of the accuracy, energy, latency, and it's also last to the different operating frequency, cell bit levels, and also the temperatures, these range, and so on and so forth. Okay, still I felt like reliability and the robustness design is critical for emerging device designs, and we still work very hard along this direction. Well, um, although we have done substantially on conventional hardwares and also emerging hardwares, and generally speaking, I think there's still a lot of challenges and in order to realize the intelligence in systems. And this is one of the examples I had in previously. For the intelligent systems, it becomes smart, but also fragile. Because attackers and there's so many points in that attacker can attack, and it's very hard to shield and protect entire systems. I guess many of you may heard about adversarial noise. Essentially, we can inject imperceptible noise into the input data and change the models and results and completely. So the prediction becomes incorrect. And our groups and have been working along this direction as well. So one of the direction is in transfer-based attack. Basically, if we have two different models and then their decision boundaries and might not align with each other, but quite and close to each other. So it's um, induced transferability across the models, and basically attacks and generate on one model can be transferred to other models. And this is where we interested how far we can go and how much we can protect. So earlier, based on these observations, and we kind of created activation attack. So the key idea here is instead of perturb the input and to change the classification results, we tend to observe some internal layers and the changes in activation, uses activation as the guidance and for the input modification. And we have very interesting observations for those designs. But understanding attack is just the starting points. What we really seek for is how to defend such attacks. So to understand the transfer attacks, and we also trying to understand vulnerabilities, like model trained on the same data set, basically captured a similar set of non-robust features. So we question ourselves, are we able to isolate those vulnerabilities? For example, if we have some source and images, and then for each source image corresponding to one target image, we can perturb the input. So the original models will produce and wrong classification results. But what lead us to the next step? The next steps, and what we do is, okay, assuming right now we have two models, intuitively, these two models will have a similar vulnerability. And in other words, if we use model 1 to classify the image, distilled on model 2 as the target labels, and then they produced a similar accuracy. Well, what we do over here is, and we present using a sample with a few submodels. And during the trainings, we encourage each submodel to classify distilled image from other submodel as virtually similar source and class label. So what happens is, as illustrated over here, if we use the regular training methodologies, and the number here represent the transferability between two models. Like 1-on-1 is definitely 100%, 1 versus 2 is pretty high as well. But through our methodologies, and 1 versus 2 or 1 versus 3, as you can see, they are not correlated, meaning they capture different non-robust models features, and therefore they kind of orthogonal to each other. So instead of like quantified results, and let me show some visualizations. This is the baselines, and the right-hand side is in 3 illustrate the decision boundaries, and this in kind of a grayish is in the target classes. So as you can see, along this in small red arrow directions, and this is the directions and to produce and wrong kind of results, and this is where we can inject the noise and for the adversary attacks. Okay, so when we combine this in 3 models, assemble this in 3 models, and the assembled model, as you can see, the decision region doesn't change much. Well, through our assembly methodologies, as I explained on the previously, the 3 submodels, and they also have this and that kind of a close to next classification results, but their decision boundaries and quite different, and their neighbor classes and could be different. And therefore, when we combine them all together, and the results, the resilience to the adversary attacks and increases and tremendously. All right, my last example is in kind of for the cameras. This is our very early work. I personally, but this is my personal favorite. So I guess, and right now a lot of people use the phones, use the cameras, and so modern digital image sensors, and as you can see, it's composed in multiple layers for various functionalities, and essentially we combine them together. Well, what we find is that all this in hardwares and kind of created a certain pattern fingerprintings. So instead of just purely utilizing the DNA solutions, if somehow we can use those hardware or sensor-based fingerprintings, and we are also able to detect the adversarial noises. And this is an the early works and we have done. So the results and here basically show that when we have an when we compare this in SPN like hardware-based detections and versus an algorithm levels, and the efficiencies can be improved in others. And of course, and for such an approach, the larger image is, and then it's producing better results. All right. So I apologize, like the talk itself is pretty rough and brief. But again, if you have any questions, and feel free to reach out to me for the discussion. Well, the overall, I think the research itself is starting from something we know better, and we tend to explore and getting to know things and we do not know but curious about. Well, a quick summary over here. I believe in future computing systems will grow along the direction of more friendly to the users. It must be automatic designs, no matter for the model itself or for the hardware designs. Also, the cost is essentially important when we're talking about the efficiencies. Although as an hardware designer or software designers, we're talking about the execution efficiency, but essentially it's leads to the cost. Well, compared to the research 20 years ago when I was a PhD student, the design scheme becomes more holistic, and people not only talking about one layers, but wanted to looking across layers and for the cross optimizations. Again, I believe in things. It's a very large domain with many applications. So there's tons of challenges and opportunities, and this could be my lifetime research. Okay, so this concludes my talk. Thank you very much for being with me, and I'm happy to answer any questions you have.
All right, thank you so much.